Hi everyone, welcome to this probability refresher for business analytics and machine learning video series. My name is Teja, and I'm gonna continue with definitions of certain properties of random variables. In the last video, we saw the definition of an expectation, and in this video, I'm gonna talk about another property called the variance. So let me just recap what the expectation was. If you remember, I'm only going to be looking at expectation. If you remember, I'm going to be only looking at discrete random variables for some time. And as I said, continuous random variables have very similar interpretation. Okay. Um, so if you remember, expectation of a random variable is nothing but a sum of the value of the random variable times the probability law that was derived for that random variable. Okay. So, for example, so these values that the random variables take, I'm going to call it the support of the random variable. Okay. In this case, for example, let's say the random variable takes value 10, 20, and 30 with probability one third, one third, and one third. Then I'm gonna just call the support of the random variable to be 10, 20, and 30. It's just for simplicity. It's just a terminology. Okay. So that was the expectation. Now, and we were trying to interpret expectation as some sense gives you some sense of the um, some sense of what this function is, this random variable function is, right? For example, if its support is instead of 10, 20, and 30, maybe it's 10, 100, 200, and 300, but with the same probability law, one third, one third, and one third. So it takes three values, right? So x takes three values, and p of x is equal to little x takes three values. So if the random variable was this instead of this guy, then the expectation of x here would be 200, whereas there it would be 20, right? So expectation is some sense of average, and also it also gives you some information about the support. For example, if the support is different, then the expectation is going to be different, and it gives you in some sense if you what is the expected or the nominal or the typical value that the function will take, given that probability law is like this and its support or its the values that it takes are like this. Okay. So that's the so similarly, we're going to look at variance, and before even defining variance, variance has a lot of usefulness. Expectation variance have a lot of usefulness. The moment you get data, even before you think of prediction modeling or any other machine learning technique, you should get a sense of your data, some sort of summary of your data, and expectation variance and a few other things help you get a grip on how spread out your data is. By appropriately defining what random variables are in that case, you'll figure out how spread out the data is. How are their absolute numbers looking like, and so on. So variance is a very useful property, and you might have, and in some subsequent video, we'll also look at covariance. So variance is a measure of the spread of the probability mass function. Okay. Of course, it also depends on the support, but it's a measure of the spread of the probability mass function. And what do I mean by that? The question is, for example, look at this probability mass function, right? The probability mass function, which is like one third, one third, and one third. Instead, if it was maybe 1 by 10th, 1 by 10th, and 8 by 10th, so this is a different probability law, right? So this probability law on the same support and this probability law on the same support, they will have different sort of spread numbers, okay, or some sort of a spread metric, okay. So this is the I guess the English interpretation of what a variance is. But formally, I'm going to use the notation VAR of x to be equal to the expectation of, now it's going to be a function of the random variable. It's going to be x minus the expectation of x, the whole square. Okay. Now expectation of x is a number, right? It's a number. It's a constant. For example, in this case it's 20. In this case 200. Okay. It's some constant. So I'm going to take my random variable, subtract it with a constant. That's another random variable, right? It's just a a function minus a constant is another function, so it is another random variable. So this is another random variable. That random variable has been squared, so that's another random variable, and I'm taking the expectation of that random variable. And as we just saw in the previous video, we don't have to derive the probability law corresponding to the final random variable. We can still use the probability law corresponding to random variable x itself. Okay, so this is the formal definition of variance. Standard deviation is defined to be the square root of the variance. Okay, and why do we like this definition? Because if you look at variance, somehow there is a x square, right? If you look at this definition, if you think of x as, let's say, income levels, okay, these are income levels, so there are some units, maybe dollars. Then the variance, the units of the variance, you can see because of the squaring, it would be dollar squared. So standard deviation is a way to like come back to dollars in a sense, but this is just a function of the variance, and it still measures the spread of the probability mass function, okay, corresponding probability mass function. So similar to the expectation, there are a couple of relations that I want to quickly state, and we're not going to spend much time trying to derive them as such, but it's there. One should you should go back and try to check whether these properties are true. So variance of let's say variance of a function which is like ax plus b. So I had the original random variable. I multiplied it with a number, maybe 10, and added a number, let's say 3. Then what is the variance of this? In the expectation case, we knew what happened, which was a came, expectation turned out to be a linear operator. In this case, what happens is this is equal to a square times the variance of x. Okay, so it doesn't matter if instead of a, so if instead of a being 10, maybe if it was minus 10, still it would be a square. So the minus and plus doesn't matter. And in particular, it's also going to get squared. And you saw that squaring is because if you look at x, x gets squared here. Okay, and b has no effect. Okay, b is gone from the right hand side. So variance of a derived random variable like this gets changed into something like this. That's the first property. And the second property is that variance of x can be written, this is just a simple identity, can be written as the expectation of a derived random variable, which is just x square minus a constant, which is expectation of x, the whole square. Okay, so expectation of x is just the expectation of the original random variable. Expectation of x square is the expectation of this derived random variable, which is this, right? X square is a derived random variable. So the difference between these two expectations, of course, the second one being square, is also equal to the variance. And you can just expand out the definition of the variance. So if you look at this, this is the expectation, right? So you can write it as sum over little x of little x minus whatever this expectation of x is. Let's call it mu for simplicity, the whole square times p of x is equal to x. Okay. So this is the definition, and you can now open up the square and do the summation. You will be able to get this equality. Okay, so let's do an example. What is the variance of x when x is Bernoulli with parameter little p? Okay, so I've just put parameter little p in a bracket. So p, for example, is, since x is Bernoulli, for example, if I have a sample space of heads and tails, which essentially means my experiment is coin tossing, x will take a value 1 when it's heads. Then the probability with which heads happen, let's say it's p, for example, p can be 1/2, right? So what is its variance? So variance of x is equal to sum over x of x minus the expectation of x, the whole square, times p of x is equal to little x, right? So I'm gonna just do this fully. Okay, so this is just going to be equal to, what is little x? Let's say it takes value 1, and what is the expectation of x? We saw last time it was little p, the whole square, times what is the probability of x is equal to x? It's p, right? Plus what is the value? What is the other value that x takes? 0 minus expectation of x is still p, the whole square, times it takes the value 0 with probability 1 minus p. So if you look at this, this is 1 minus p, the whole square, times p plus p square times 1 minus p. Okay, let me take a few terms common. So 1 minus p is common, so let me take it this way. Then I'll have 1 minus p, actually p times 1 minus p is common, so I'll have 1 minus p plus p. Okay, 1 minus p plus p is nothing but 1, so this evaluates to p times 1 minus p. Okay, so that is the variance of a Bernoulli random variable. So let's say if p is 1/2, then this turns out to be equal to 1/4, right? If p is let's say very close to 1, so if I flip a coin, it almost always lands as a head. Then this is going to be very close to so if it lands ahead, let's say p is 0.9, then 0.9 times 0.1, which is 0.09. So, and when p is 1/2, this is 1/2, 0.5 times 0.5 is 0.25. Okay, it's 0.25 and 0.09. So as p is getting higher, the spread or the variance is getting lower, right? Or as the moment the p is going away from zero point 0.5 closer to 0.9 or closer to 1, the variance is decreasing. You will also see that as p is going to 0, the variance again decreases because this is just a simple symmetric function. So the variance seems to be high when the coin is unbiased, or as in if it's the probability of it landing heads is the same as probability of it landing tails. Okay, so just in addition to this exploratory statistics that you would collect when you get data, you would look at expectation and variance of your certain features like age, income, and stuff like that. If you have certain data like that, variance is also useful in terms of, for example, in linear regression. You do the linear regression, you get some coefficients. You can actually think of these coefficients as functions, coefficients as actually random variables. Okay, if these coefficients are random variables, they can have expectations, they can have variance as well. And if they have variance, then it helps you understand the variability in your prediction model. Okay. And so when you look at linear regression, and you can also think of how do I think of variance of objects in there. So you have to interpret the coefficients, for example, as random variables, to interpret inputs as random variables, or maybe outputs as random variables, and stuff like that. Okay. One last thing in this video, I'm going to just describe what a conditional probability mass function is. Okay. Conditional probability mass function is nothing but the original probability mass function conditioned on an event. So think of a random variable. So let's say the probability mass function corresponds to a random variable x. Okay. So remember, x was a mapping from omega to some numbers. I'm going to use 10, 20, and 30, a simple example. And omega is, I'm just representing the sample space as a box. Let's say there's an event A. Okay. So I can think of a conditional probability mass function as the probability of x taking a value x given A. Okay, this is a notation. It just means that it just means the same conditioning as before, where, and you can see that by expanding this out. This is a probability of all the omega in my sample space such that x of little omega are now elements of my sample space or outcomes, is equal to x, right? So this is an event given another event, right? So this is an event. Think of this as event B. The probability of event B given probability of event A. This we have seen before, right? So this is this is just a way to kind of motivate what a conditional probability mass function is, and And so if you want to think of conditional, so x given another event A, you can also look at conditional expectation. You can also look at conditional variance of x given A, where A can be any event on the sample space. And now this description is quite abstract. I didn't give you an example, but I just wanted to say that the computations are the same. What changes is the probability mass function just changes. Okay, it's a new probability law instead of the unconditioned probability law. And with the new probability law, for example, previously, let's say with 10, 20, and 30, you had one third, one third, and one third. Maybe after conditioning on this event, these numbers became one sixth, one sixth, six, 4/6, and two thirds. Then so with you'll just have a changed probability law, and you can still compute expectations and variances according to this law instead of the previous law. Okay. So this is just about conditioning our conditional probability mass function. That's all for this video. Thank you for watching.